that's all I've really got for logistics. It's simple. Charles, over to you.
Awesome. Yeah, thanks for setting us up, Harrison, and thanks as always for organizing this and for making a really sick library. Yeah, so I'm Charles. I studied neural networks at Berkeley, and actually relevant for this topic, I went into grad school thinking I was going to study probabilistic graphical models and Bayesian networks, and then everything changed when the neural network nation attacked, and this style of artificial intelligence and machine learning kind of faded as you know big networks on big data kind of took over. And so the folks that we have presenting, talking at the webinar today, David, Shunyu, and Ted, have done some really excellent work, like bridging that gap and sort of recognizing in the techniques that people have been doing that have had empirical success, where they can be understood with those past techniques, and then also where the work that went into building those past techniques actually turns out to be useful for thinking about agents, thinking about chains, providing a framework. So I'm really excited to hear from all of them. And I'd love it if we could just get introductions before we dive into the slides, maybe from David first.
For sure. Thanks, Charles, and thank you, Harrison, for the invitation. I'm looking forward to getting to talk with all you son. Yeah, so my name is David Doan. I'm currently a researcher at OpenAI on the AI scientist team, where we work on things like the code interpreter and data analysis for ChatGPT. Previously, I was at Google Brain. I mainly did work on AI for science and reasoning over there, so a bunch of work on proteins, a bunch of work on language models to solve scientific problems. So Minerva is probably the best known one out of that. And then my last work there was on model cascades, which was how do you chain these things together and how do you actually then run inference over them, where you ask questions like, let's say I have chain of thought model. I want to find a chain of thought where at every step the verifier is happy, and at the end you get the answer that gets me the right answer. And you have all sorts of inference methods which are propagating now, simple things like self-consistency, or more complicated like tree of thought where you do beam search on top of it. But generally it's how do you specify a model using programming language. I use the formalisms of probabilistic programming. And then how do you actually then search against it to satisfy some constraints? So I think of this as like a declarative, the same way you have SQL queries where you want to specify constraints, you want to be able to specify constraints against your model that you've already written.
All right. Thanks for that intro, David. And we'll kick it over to Shunyu first, and then Ted.
Hi, my name is Shenyu. I'm a PhD student at Princeton. I've been working on transforming language models into agents. And you probably know me through work like React or Tree of Thought, this time Koala. And I'll give it to my colleague, Ted.
Awesome, thanks. Yeah, so very excited to be here today. I in a former life was a research engineering manager at Uber, working on signal processing and machine learning techniques to do things like detect dangerous drivers and various things like that. I am currently finishing up a late in life PhD because I got interested in social learning and sort of distinction between gradient descent versus reading a textbook. And so that had some fortuitous timing with the advent of large language models. And so most of my PhD research, half of my PhD research is psychology and sort of looks at the cognitive factors underlying social learning from other people in this very interesting sort of game theoretic setting that is real life. And then the other half applies those insights to AI in various forms, with the most recent thing being obviously this Koala paper, which we are very happy to talk about today.
Awesome. Yeah. So I think Shunyu, you have some slides for Koala, and go ahead and present those, and we'll be watching. The folks on stage will pop in with questions, and we hope to encourage folks to post questions in the Q&A section as we're going, and keep like a nice vibrant discussion on agents, on like probabilistic programming and other frameworks for making language models good and more powerful. Yeah. All right. Take it away.
So can people see my screen right now? Yep. All right. So are we gonna do like first the slides and then we do the QA, or we do the QA within the slides?
Yeah, I think we'll have lots of questions and tangents off the slides. So yeah, tree of discussion off the slides.
Okay. So I'm gonna first talk about the motivation and the formulation of this Koala paper, and Ted is gonna talk about what are the implementations from both CoALA and AI, and what are the empirical actionable insights from this paper that we can talk about. So Ted and I did this paper called Koala, which is short for cognitive architectures for language agents. And the motivation of this is simple. We have language model, it's great, but it has problems. That's why we build language agents. But the question is, there are many ways you can build language agents by how you write code to make use of the model, right? So, for example, some of the simplest thing we can do is React, where you have this thought, action, observation, thought, action, observation loops. And at the time when I did this, last year, the motivation is really clear. Basically, you just need to combine reasoning and acting to make it better than reasoning only and act only. But then things got more and more complicated. So for example, you could add, a memory, a library of skills. You can add retrieval. You can add, self-refined reasoning. You can also add, multi-agent interaction. You can add reflection and planning and so on and so forth. So I think the motivation is just we have this, explosion of concepts and techniques and components when we are building, chains or agents with large language models. And sometimes it's exciting, but sometimes it's overwhelming, right? Like, how do we even make sense of so many things that's going on and so many techniques? And how do we know, what is the general trend of this direction and how to move it forward? So a quick analog to motivate Koala will be to look at, how do we make sense of circuits, right? Because if you think about each chain or each agent is kind of like a small circuit. But the problem is when you have a really complicated real-world application, this circuit could be really, really complex to make sense of. And oftentimes, when I write code, I feel like sometimes I'm writing code like this, but you want something like this, right? You want a very systematic principle or abstraction to write things, and that's also part of the motivation of LangChain, right? But we know, for circuits, like a very good way to make sense of them is, we have things like von Neumann architecture, right? This architecture modularize, each component and say, hey, this is doing this is doing that, and there should be some high-level principle, how those modules should interact with each other, and that's probably how we switch from, those like complicated digital circuits to actual computers, right? And the motivation leads to this idea that if you want to make sense of all the crazy language agents nowadays, you should also have like an architecture viewpoint where you think of language model as a component, and then you think of a higher level architecture on top of it. Just like CPU is just a component for a larger computer architecture. So we have this paper called Cognitive Architectures for Language Agents, and it has a lot of pages and content. What is cognitive architecture? Why it's related to language agents? How do we formulate language agents through cognitive architectures? And then what is the insight we can get from this connection? Given the time, I'm just gonna quickly go over the framework, and Ted is gonna talk about the insights. So let's just skip all the interesting history stuff.
Wait, Shunyu, this is one of my favorite parts, the like connection back to classical good old-fashioned AI. I must object to skipping over it.
Okay. So maybe a minute for the history, right? So a quick overview of history, right? So if you think about what's happening in the first half of 20th century, people realize a lot of fancy stuff are just simple manipulation, right? For example, if you think about mathematics, you can just build that on top of symbol and manipulation rules. If you think about logic, if you think about even computation, right, it's just some sort of simple manipulation. So if you have like a system of like rules, right, you can manipulate symbols in that system, and then you can get a lot of interesting things, right? You can get a proof for 1 + 1 = 2, or you can get a computation machine for any function that's computable or whatever. And but I think what was really interesting is around 1950s we start to actually build physical systems that can actually manipulate symbols. Right? That's why that's computers, right? And that's why we have those symbol systems that can actually be implemented in the physical world to interact with the world, right? So this is like a very simple manipulation system to describe what is an AC, right? And what's really cool is now we have a way to ground that into an actual AC to make it work in the real world. And that's what kind of happened, in the 60 years ago when AI just happened. You have those like simple manipulation rules used toward real world application, and that's what that's kind of the invention of symbolic AI, right? So because you need to interact with the world, you need I/O devices, because there are many possible rules. So you need like a priority over those rules, and because there are complicated information, you cannot possibly just store that into the CPU, right? You need some memory mechanism, and if you take all that in, you develop this algorithm to use simple manipulation to interact with the digital world. You get this cognitive architecture, which is kind of like a hallmark of symbolic AI around 1980s, right? And that's basically just a very complicated software that has many complicated components, to turn symbols, to manipulate symbols in a very principled way. And at the time, you have many architectures for cognition, and the claim is that they can both do very complicated real-world applications, and they can also help explain human cognition. But why symbolic AI kind of had a winter at the time? Because the world is too complex, right? That means you need to have many rules, and it's just not feasible for humans to write all the rules. And also the world is stochastic. That means the rules can be fragile, and you need some way to deal with randomness and stochasticity in the world. And that comes in neural network, So we all know.
Could we go back a slide?
Yeah.
So this, like the things you're showing on this slide, though, like Koala architecture on the left, and something like a model of the brain on the right. These are the equivalent of sort of like that von Neumann high-level diagram.
So actually, there are two different cognitive architectures at the time. So the left one is called SOAR, the right one is called ACTR. There are just many different ways to structure this system, and different people propose different architectures.
Mm-hmm.
Yeah, there's actually, I think, something like maybe 300 known cognitive architectures out there, some of which were intended for AI, some of which were intended to be these very accurate models of the human brain used primarily for psychology. And so there's the field of cognitive architectures is itself an enormous thing.
Yeah, I just mean like if I want to connect to like my knowledge of how computers work and use that to understand what you're doing here, it's like I should imagine like a printed circuit board in the place of that, or yeah. But
you can imagine there are different computer architectures at the time, and basically there are different system level protocols or abstractions for those like complicated software, and different people just propose different architectures, and for different applications, basically. Yeah.
Random side note along the comment about there being like 300 different cognitive architectures. I feel like that's kind of similar to like the number of like agent frameworks that there are today. Like there's a big explosion of them. But I do think like, you said that there were so many because they had different considerations. And I think that's true of the agent frameworks today as well. Like there are a lot of different things that you can do with language models. And so it kind of makes sense that we'd see this big explosion of similar ways of trying to think about it, but slightly different and slightly different purposed.
It's
Totally.
true, but I think that's actually it's funny because it both points to the amount of interest and the diversity of interest in cognitive architectures, but it wound up severely handicapping the field as well because everybody wound up working in their own framework. And so there were a number of efforts to kind of reconcile this and come up with like a common model of cognition that was sort of shared across all of them. But definitely, I think standardizing early would be nice because then you avoid this kind of fragmentation and 1,000 variations on a similar theme.
Yeah, I guess some degree of diversity is great, but if everybody just work in different concepts and terms, that might be an issue for the field.
Yeah, I think we're all grateful for the x86 instruction set and not having to think about that level very often.
Yes.
Yeah.
Yep.
On the front, I also want to kind of bring in David's perspective on this. So the way you present it in Koala is these like production system perspective that comes from cognitive science, comes from things like SOAR, and connects back to Alonzo Church and the early computer science. The perspective in David's paper is coming from probabilistic programming, and the production rules there are, or rather than production rules, it's about conditional sampling. So David, I'm curious, like how do you see that conditional generation view intersecting with the like production systems perspective from the Koala paper?
Yeah, first of all, can y'all hear me? My mic was being a bit funky. Great. Yeah, also I love we can look at this diagram from 40 years ago and be like, oh, someone published that like a month ago. But this is the fresh and new. Right, so one thing I'll note, probabilistic programming comes a lot from the cognitive science world. Like the group that's probably best known for it is like the Tenenbaum sort of lineage group and Noah Goodman at MIT and such. I think sometimes the distinction between inference and model can get a little bit fuzzy. Like your inference itself can look very much like it is just another long chain or program that's running something. Within something like cognitive architecture, I would tend to, I sort of struggle to think about inference at the scale of running a full agent. You can, would look like running like essentially the agent many times in parallel, which doesn't quite work in the real world. It does work if you have some simulation or world model where you can sort of do planning inside. The place where I think it is useful is more like as a subcomponent inside of one of these cognitive architectures, like perhaps the planner is running something like this inside of it. I have not explored like sort of doing this to full agents. You can, so an example would be essentially you write your agent as one of these programs and you have a lot of tasks where you want to succeed. And essentially the inference question you have is, I want it when I run my agent, it gets the correct answer. And what this ends up mapping to is sort of like a, I have this program, how do I train my program? I can't take gradients anymore. I can't, like, you can do RL type things. And there's a host of techniques, but they all sort of are somewhere on the inference learning boundary. But yeah, so that's what I think about is either as a way to implement submodules inside of these larger systems, which are very dynamic, like sort of, honestly, probabilistic programming doesn't transfer well to this like asynchronous many parts, like actors interacting. Like there isn't sort of a clean abstraction there. And two, if you do have this system, you can roll it forward. It's like, okay, how do I train it? Or like, how do I like train these subcomponents such that when I run this thing forward, we get the right answer?
Yeah, Shunyu and Ted, any thoughts on like that perspective, how it aligns or doesn't align with you?
I think one of the things I'm just going to jump in because I'm so excited about this. One of the things I'm most excited about is as we get these sort of more deliberative or structured classical planning algorithms in language agents, I think that there's a very clear niche where the sort of forward simulation rollout component can be handled by, probabilistic programs where you can reason about the consequences of an action in a nice way. And then you maybe want to actually evaluate whether that's a good outcome or not using the LLM itself. But I do think that there's that's like, again, one of the directions that I'm most excited about, because I think that these two literatures, like reasoning with language versus reasoning with, these nice structured probabilistic programs, there's been really interesting work there, but there hasn't been like a full unification. And I will say also things like SOAR actually do, like these OG cognitive architectures, they do explicitly carve out a like simulation, like the importance of simulation, forward simulation for reasoning. In language agents today, we've mostly done that with just the LLM itself, but I think that this kind of probabilistic thing is really important.
Yeah, I think my response is actually just the next slide. So let me just move to the next slide.
Yeah.
Yeah. So we all know language model is great, and one way to think of language model that we claim in this paper is you can think of them as like a large implicit production system that can turn a lot of inputs to a lot of different outputs, right? And because it's large, and because it's implicit, and because it has stochasticity by nature, it actually just solves, the issue of the good old-fashioned symbolic AI's biggest problems, right? You have this large knowledge base to deal with complex issues, and is robust with regard to randomness by nature, and we have built all those agents, and now we've seen those architectures, right? And I think my answer to your previous question is, I mean, the simplest way to think of everything that we are building out is just you have a Python program that calls some large language model to do something, and the question is how the code itself should be structured, right? And you can structure the code by probabilistic programming kind of philosophy, or you can structure your code by some other classes and objects and abstractions. But at the end of the day, you're just writing some code to use the language model, and the issue is how can you most efficiently or cleanly write the code so that it's easier for both the developer and for future development. And I think the main idea for our paper is one way you can try to write your code better is to think of the abstractions proposed by those cognitive architectures, which we will see in the next couple of slides. Okay, so let me just quickly go through what we're proposing, right? What is the Koala framework? So this figure looks like this, and this is a little complicated. So to simplify, this framework, you just need to know 3 concepts. And once you know the 3 concepts, you can just specify any language agents. So they're memory, action, and decision. Okay, so what is memory? Memory is just where you store information, right? And one of the key idea from Koala is you should have a short-term working memory that stores relevant information for the current decision cycle. But this concept will be defined later. And you should also have some long-term memories, right? So they could store your experience, like what the agent has interacted with the word yet so far, and you can store knowledge, right? So the agent can reflect on his experience and propose some knowledge, right? So and furthermore, you can use those knowledge to actually define some actionable things, right? For example, like you can fine tune the language model, or you can write some code to actually interact with the words. So you have those modular long-term memories to store different kinds of things, and you also have a short-term working memory to store things that is useful for the recent time. And the next important concept is just action space, right? So once you have those memories, what this agent is capable of doing is defined by this action space. So interestingly, action space is a fundamental concept in reinforcement learning, where every RL agent has an action space, but it's not a very typical term for language agents. So I think what's different here is for RL agents, the action space is defined by the external environment, right? So if you're playing a tower game, then action space is just up, down, left, right, and you don't have a say in what is action space. But here, action space is actually part of your design, right? So you have those external actions that interact with external environments, and we call them grounding actions. And that's basically the same with all the RL agents. But more importantly, you also have those internal actions that interact with internal memories. And so if you're reading and writing working memory, that's reasoning. And if you're reading long-term memory, that's called retrieval in Koala. And if you're writing to the long-term memory, that's called learning. So you can see there's like a very neat categorization of all the possible things that this language agent is capable of doing, and is both interacting with external environments and internal memories. And then the natural question is, once you have this action space, how does the agent choose actions from this action space, right? And that's called decision making in Koala. And the idea is, imagine all the actions that agent takes, right? Like action 1, 2, 3, 4, 5, 6 until 10. So we split those actions taken throughout the time into cycles. And in each decision cycle, there is this procedure that the agent plans an action, then execute the action. But what is important here is during the planning phase, you use reasoning and retrieval actions to propose or evaluate actions iteratively. So if you think about things like tree of thought, it's just using reasoning to continuously updating the working memory. But at the end of the cycle, you should decide on a learning or grounding action. And learning and grounding are special because learning changes the long-term memory and grounding changes the external environment. So they are more kind of like important actions that you should just decide on. And in Koala, each language agent should just plan, then execute, plan, then execute, plan, then execute, so on and so forth. But how do you plan? There's a lot of varieties that we can talk about later in this webinar.
And so just to clarify, so like the planning and executing, both of those can take different actions, but you're saying like if you take kind of like a retrieval, and actually if you go back one slide, so you've got planning and execution, and then you've got this action space.
Yeah.
And so which of the action, so like just to make it really concrete, like which of these actions here correspond to like planning and execute if you take that action?
Yeah, so if you look at this figure, right, so we use reasoning and retrieval for planning. And the execution stage, we just decide on a learning or grounding action and then just execute it. And the split is because, reasoning is only updating the working memory, and retrieval is only reading from the long-term memory and loading into the working memory. So they are kind of the, more like simulation kind of actions. And learning and grounding is what actually changes the long-term memory or changes the external environment. So the intuition is that if you really are changing, either your long-term memory or you're changing the environment, you should be careful, and you should first, in the working memory, try to simulate what will happen or evaluate, what is the best action and so on and so forth. And in some sense, changing the working memory is constant and it's not that harmful, and you can do that more frequently or casually. But if you're changing the environment or changing your long-term memory, you should be more careful, and you should use planning to decide on such action.
I think one other way to think about it is this, like, sort of what is a is the planning actions are used to support short-term decision making. So you have some context, you're in some environment, and your question is like, what do you do? Whereas a learning action is intended to update your behavior in some future unknown context. And so that's really like where you start to get generalization. And so the decision to sort of commit something to a long-term memory store is specifically in the context where you think you're going to need that again in the future. So reasoning produces like, it updates your sort of existing, like what's going on right now, but then you might be like, oh, that's a useful. So for instance, in reflection, you decide, okay, I have this thing happen to me in the environment, and that's something that I should really actually remember at some unknown point in the future. And that's why learning is a special internal action, because it's updating a persistent characteristic of the agent, as opposed to just generating more knowledge to be used right now.
I think a useful analog here will be something like AlphaGo, right? So basically, if you think about how AlphaGo works, right? So before AlphaGo takes each step, right, it will simulate a lot of like multi-color tree search, simulate what will happen if I take this, the opponent takes that, so on and so forth, right? But at the end of the time, right, it will pick one grounding action, which is pick up a stone and put it somewhere in the board, and that's kind of the grounding action. And intuition is kind of like, before you do such a grounding action, you can do a lot of like internal simulation in your working memory, but you should plan for each kind of the grounding action, because once you commit this grounding action, then the word is changed, and you cannot undo that. Whereas for reasoning and retrieval, you can easily just simulate and undo like everything in your mind or in your working memory.
Mm-hmm. So I've been seeing some questions, and I have some questions of my own about memory, like how this is parceled out, how to think about it. So one question that I like from Dhruv, what's the basis of deciding what goes into semantic memory versus episodic memory for an agent? How do we split that up?
Ted,
do you want to answer, or?
Yeah, absolutely, sure. So the basic idea is these different forms of memory are specifically designed for different kinds of prior experience. So semantic memory is like facts about the world. So you and I know that Joe Biden is the current president of the United States. That's a fact. On the other hand, I know that I read something online about Joe Biden earlier today, and that's episodic memory for me. So if you take raw experience, if you literally take the agent's perceptual experience and store that text trace, that's episodic memory. And so that's really rich because it contains everything the agent experienced. But that also means that it's super bulky and kind of hard to work with because it's this really raw form of data. And so semantic memory could be generated by, for example, reasoning or reflecting on that experience. So that's some work that Shunyu has, is you take this gigantic trace of experience, you extract some specific factual information that you think is going to be useful later, and you store that back to semantic memory.
I see.
Same deal with generative agents. They use their own prior experience and reflect on their, like, I'm a this kind of person, and then they store that in their semantic memory.
Mm-hmm. So if I'm Joe Biden and I win a presidential election, that's an episodic memory, which I might store as a fact that is Joe Biden is president of the United States.
Right. You could. So you don't have to. Joe Biden doesn't have to wake up and think, have I ever been elected president? Right. He doesn't have to recall the memory of being elected president. He sort of knows factually he's the president. And so that's maybe the best. Yeah, exactly.
Are there?
Hopefully he doesn't have to recall. I mean, that's sort of I should have chosen a more neutral topic, but anyway.
In terms of like the data structure in which you're storing these memories, like, do you think there's a distinction between the best data structure to store episodic memory compared to semantic memory?
Yeah, that's a very good question. I can take on that. So if you think about system level abstraction and the lower level components, there is often this kind of disentanglement in the sense that here I think the key idea is you should have different types of memory for different types of data. But for each of the memory component, you can choose what is the best way to implement that depending on the application. So it's possible that for both episodic memory and semantic memory, you are both implementing that in some JSON database, or you choose to use implement semantic memory with some vector data store, and then episodic memory using some SQL database. I think the most interesting thing is that you have this disentanglement of implementation and abstraction, and you can choose for each component what's the most suitable way to do this depending on the application.
Mm-hmm. Yeah, I like that perspective, but I actually want to bring David in to complicate it a bit, which is that in like language model cascades, it feels like the procedural, like the LLM is not just the procedural memory, right? It also might be where semantic memory comes from. It might be like, yeah, so it kind of like straddles at least that divide. Do you see that as well, David, or do you, or should we like try and rip that out of language models? Yeah, how do you see those interacting?
I mean, I guess I do want to emphasize that at the end of the day, it's just language models inside programs, and you can do anything inside this program. So as much as possible, we should be interacting with things that are good at remembering, and language models are not particularly good at remembering. Like there's sort of, I know, it's a problem. Yeah, like you can try to put things directly into the model, but in general, I think we want to rely on databases or rely on tools. I'd say that the larger point about model programs here is that it's you have a program that uses models inside of it. It may use tools, it may use databases, and then you want to be able to train it, or like, and part of that action might be using a search engine. Like that's totally valid as part of a cascade, right? And there's a lot of things where the right tool for the job is not going to be the model itself.
That said, I'm also like increasingly interested in the this like interplay of memory and reasoning, and I think it's still an open question as to like exactly how people retrieve relevant memory for something. Like that's definitely a crazy thing that happens in our brains. And I personally think it would be super interesting to try to do just some kind of like spreading activation model over a dense retrieval, where there's no a priori reason why you need to split procedural and semantic and episodic memory into different data stores. In theory, you could have one vector data store that embeds knowledge in text, and you could just retrieve, you could use your current context, do a nearest neighbors lookup, pull a bunch of stuff and say, did I get a procedure? Like, did I get some action that I could take? If so, I should consider it. Did I get some piece of semantic knowledge? If so, I should add it to my context. Did I get some episodic information, in which case I should reflect on it in the current context and decide how to act? And so you could imagine some world where there's actually like much less imposed structure on the planning process. And instead it's just a sequential process of retrieval, reasoning, and then when you reach a certain threshold, taking an external action. And if you look at existing models of memory and decision making in people, that's sort of the state of the art.
That does also point to just this spectrum in these things generally of like, on one extreme, it's just going to be one big model is going to do everything. You don't need any of the scaffolding. And the other extreme is like, we need programs that are highly structured, provide extreme scaffolding, like have verification, annotation everywhere. And it may be the case that, the GPTs in 8 years, like they do everything that your computer can do and they don't need any of these tools. Yeah, but why make it hard for ourselves?
That's right.
And it's also just, you can have, at least in the current world, you can have much higher assurances if you have this scaffolding. And you're like, okay, it retrieved the thing, it put it in the context, and then it generated. And then maybe you even have like a little subsection that's like a little side model that says, did what it generate actually have anything to do with what it said? Mm-hmm. And maybe at some generate, and you'll be 100% sure that it's going to be right. You don't need that verification. But for the moment, it helps to have this additional filter.
Yeah. That's right. And there's something to be said for the modular, like even if the human brain does it all in one gigantic vector store, it's a lot easier for us to design and reason about distinct ones, at least for now. But David, there's to your point, there's a great section, and I think at the very end of the paper, it's like one of my favorite parts, largely inspired by Shenyu, about like what changes with GPT-N, like how do we expect this interaction of the agent code that we write versus the model to change as they become more and more capable. So I can pick up and talk a little bit about the sort of what Koala buys us in terms of like, why is this actually useful moving forward? So I think the first thing which Shenyu talked about a bunch is we have this proliferation of really awesome work, but it's sort of hard to understand or compare. And so, it's actually quite straightforward and I think helpful to kind of cast these agents into the Koala framework and then kind of ask, how do they actually vary along these different dimensions? So, they use different forms of long-term memory. And in fact, many of them don't actually use any long-term memory, which is quite interesting. They have different forms of external grounding, so they're designed to be deployed into different environments. They have a wide sort of variety of the richness of their internal action space. So, React, as amazing and impactful as it is, it's really just sort of reasoning about the current context. It's not doing this kind of lifelong learning and retrieval from memory, whereas these more recent agents are actually sort of integrating and synthesizing, or Reflexin is integrating and synthesizing its experience in a much more sort of long-term way. And then finally, you can look at their actual decision-making procedure and ask, are they really sort of doing this fully fledged deliberative reasoning process, or do they look more like reflex agents, Q agents that are sort of proposing and selecting a single action at a time just based on the probability from the model itself? And so I think what we see just in constructing this table, what we really saw is there's a lot of opportunity here because all of these agents can be sort of subsumed by the Koala framework, but none of them instantiates anything close to a complete Koala agent. And so we're really excited about the sort of future direction of building this out a little bit more. And so just to give you an example, this is the sort of section on learning in Koala. And I won't try to read any of this, but I think it's worth noting that when you see learning as writing to long-term memory, as opposed to, reinforcement learning or specifically like writing to semantic memory or any of these individual things, you can immediately see that these are all sort of different solutions to the problem of how do you modify your behavior in the future, given some existing experience. And that allows you to sort of understand and reconcile when it might be useful to implement one form of learning versus another. And in particular, it actually, this sort of process of reviewing the literature highlights a ton of gaps where there are a lot of methods that have been developed outside of language agents that just haven't actually been attempted inside language agents yet. And so we really think this is an exciting future direction of research, which is just leveraging all of these known techniques in the context of language agents.
For example, can an agent change its own code? I think there are going to be some new work coming soon, but yeah.
And so the last author on this paper is Tom Griffiths, who taught me everything I know about cognitive science, I think. But his perspective has always been this like computational Bayesian perspective, which is about like rational use of computational resources and attainment of goals. And one reason why I was excited to put like David in conversation with this paper was that the perspective in language model cascades is probabilistic, is Bayesian. So, David, what do you think the prospects are for using that kind of framework to like kind of maybe put all these things on the same footing? Like it's all Bayesian updating, or it's all, KL divergence minimization or something.
Yeah, so let's see. I mean, one perspective is just that all of RL that works ends up kind of looking like you're doing a bit of Bayesian inference. Like it's a bit reductionist. Like this is sort of the argument you often get. Everything is like, well, everything that works, like if you squint, like it's kind of Bayesian. I'm not going to necessarily make that argument here too much. Let's see.
I guess like it succeeds or fails insofar as it's like useful for clarifying things, or so like putting things on the same footing, or like helping you come up with new ideas.
Right. So, okay. So in a way, the form of your cognitive architecture is it's forming the prior over what are things that your agent can do, right? Like if you don't have a semantic if you don't have this internal memory, then it's not going to learn over a long time, and that's restricting the sort of classes of thing it's going to be able to do. So that's just one perspective of the sort of scaffolding, sort of structures you put in place, set the stage for how wide of the tasks and like what can this agent evolve into when you actually run it in the real world. There's also like, as you train it, like, you know, I don't think there's been much work yet on training these agents using reinforcement learning, for example, largely because people are using black box models where they're just sampling. But I'm surely people are going to start doing things like policy gradient, et cetera, which, you know, is basically doing some form of Bayesian updating on the weights. Let's see. I don't think there's, I think there's, you can sort of engineer your way forward, though. I don't necessarily think you have to approach it from the perspective of you are explicitly optimizing like free energy or something. Like,
yeah,
there's a lot of things that are very obviously we need to fix, and in doing so, maybe under the hood they're doing something like principled from that perspective, but you can justify them very easily by just like, this is a problem, we're going to fix it by introducing this component, and engineer our way to like pretty intelligent and robust systems.
Yeah, RLHF came before Ethan Perez's paper saying RLHF is KL divergence minimization, and that might be, we might have practiced leading theory for a long time.
Yes, I agree. And I mean, the hope is that these perspectives do actually provide something useful. Like I do actually think that the like inference perspective makes a lot of algorithms apparent, like starting to do things like beam search on top of your model, or starting to do some sort of search, like what are you actually trying to maximize, or like how do you actually take information maximizing moves, for example. Like if you actually try to like not just say from the model, what do you think we should do, but it actually like plans against a world model. And it's like, okay, these are the places I have uncertainty. Based on that uncertainty, I'm going to go gather more information. Like that's where you can start to link up these things and take ideas from optimal experiment design. A lot of this stuff, the way I think about it is actually in terms of there's simulation-based inference, which is sort of dual to probabilistic programming in a way. And that's, you have a system, you want to run it forward. You have some things you want to be true or that you've observed to be true. So in this case, it solved the problem, or it stayed within some particular bounds. And you're basically just fiddling with the parameters. You're trying to be able to run it backwards. Like when I run this agent forward, it gets the right answer. I want to run it backwards. And the place that you have saw this in like the real world, people may have heard of like the black hole, when they were imaging the black hole, for example, or the Large Hadron Collider. Like they built the Large Hadron Collider and they ran it, and they had what the standard model predicted about the Higgs boson, and they couldn't change what the Hadron Collider actually output, so they had to like fiddle with the parameters of the standard model until it fit, and that's how they work out all the parameters of the Higgs boson. It's sort of a similar thing here. It's like, well, we can't change whether it's going to get it right or not when we run it, except by fiddling with the architecture, fiddling with the parameters. And this can be a perspective on how ways, and that admits a ton of different algorithms for doing that.
All right, I wanted to leave a few minutes for Harrison to talk about LangChain and how they're looking at Koala. So I think I'll kick it over. That was also our most high.
Let me say just super quickly. I have one thing that I do want to say, which I think might be helpful for this audience, just to kind of wrap stuff up really quick. So I think one of the things that Trini and I are excited about here is just like this idea of having a modular design pattern is really helpful for people who are doing research on models, because it allows us to actually compare these different methods in a systematic way. I think it also is really helpful from an implementation perspective, just from this perspective of reducing technical debt in these complex systems. Whether you're at a single company and you have some internal model repo, language agent repo that so that your like customer service agent isn't using a totally different data source from your, you know, whatever agent. And then also I think this structured framework for deliberative reasoning is nice because it leverages these different forms of learning. So you can pull in different kinds of memory in the planning stage. And then also, as I was mentioning, like, I think that is really interesting. This idea of using a mixture of language-based and simulation-based reasoning is a really nice potential path forward for these systems. So, yeah, that's it from us. Thank you.
Awesome. Yeah. So yeah, your second point about mixing different kinds of learning, simulation, and language-based reasoning really dovetailed with the perspective that we got from David and from Cascades. Your first point about reducing technical debt and making it easier to engineer these systems, I think, connects with Harrison's perspective from building LangChain.
Yeah, and I mean, one of the conversations I had with Shinyu right after the paper came out was trying to map some of kind of like the LangChain chains and agents into this framework and kind of see how like what that mapping kind of looks like. I think like and I know we're a bit short on time, so I'll maybe just share some thoughts, and then I'd actually love conversation. We probably won't have time to discuss anything, but I think like what in chatting with Shinyu, I think one. And again, like LangChain's focused on chains as well as agents, so it's not purely kind of like agent based. But one of the big kind of like, but almost because of that, one of the big things that we're interested in is like, what is the pattern for like interacting with tools and taking actions look like? And I think to that end, we draw a little bit of we draw a little less distinction between kind of like internal tools versus external tools. And so to just give one of the concrete examples that I was going back and forth with Shinyu about, for like, let's say like the fact-based episodic memory, like if that's something that I maintain myself, or if I use like Wikipedia as an external form of that, how I interact with that could look very similar. Like I could always query that. I could query that kind of like with an arbitrary query multiple times, like React. And so I think from like the interaction patterns and the code patterns there, it can look very similar between like an internal tool and an external tool. And I think Shinyu brought up some good points around if it's an external tool, you might want to handle kind of like edge cases more. It could like change its form under the hood. If it's purely internal, it could like stay the same state. But I think like and those are very good points, and I haven't kind of like fully grokked them and thought about them yet. But I think like on the surface, like interacting with internal and external can look fairly similar. And so I'm just going to share one diagram, and I shared this with David last Friday, and I don't think it's perfect, so I don't love it, but I'm going to share it just because I think so. This is something that we've been thinking a little bit about, and it kind of like runs the gamut of like code to like pure agent, and then there's a few different dimensions that we're thinking about, and so the first two I think are pretty straightforward, and then the third one I don't really love, but I don't 100% know how to describe it better. The first one's like just deciding like what the output is. So like using LLMs, you start to have like the language models start to decide some of that. You can do that with like a single LLM call. You can do that with a chain. Then there's like deciding what steps to take like as part of your chain. And so if you're making just a single LLM call, or if you have a chain, the steps are kind of like concrete. Like you're going to do this, then you're going to do this, then you're going to do this, and there's pros and cons to that, right? And then as soon as you start letting and a lot of this, by the way, the like code here, I think this wraps really nicely to some of like the procedural stuff that Shinyu was talking about. So like what's the code behind the application? Then when you start letting but as him and David said, it's really about like, yeah, code's interacting with the language model. What does that code look like? And so then like when you start letting the language model decide what actions you actually take, that could be, we draw a differentiation between kind of like routing and some type of like state machine. The main difference being the state machine's in a loop. And so then you can start to have cycles. And with a router, you don't have those types of cycles. And I think once you start adding cycles, it's kind of like, you know, a while loop while you're deciding actions. And then the difference between state machine and agent, this is a lot of what David and I were talking about, and I don't think I have a super clear way to describe this, but I guess like I'll maybe show like an example of what I mean by like a state machine, which is this diagram from sweep.dev. And you can see here they like break down the steps into like very clear steps where there's a planning step and then an execution step and then a validate step, and they cycle between them, and then at some point they're done. And if you compare this to like something like AutoGPT, you're kind of like implicitly asking AutoGPT to do all of this in sequence, but you're not like hard coding that it has to do this. And so I don't really know how to describe that, but I think like that's the difference that I'm trying to get at, and I'd love any thoughts on all of this. And I also know we're short on time, so maybe these thoughts will have to come at a separate point. I've made Charles silent. I don't know if this is good or bad. I've never seen it before.
A lot of internal actions going on there. Sorry. Yeah. So I guess
Show your work.
yeah, to close it out, let's think step by step. So yeah, I really enjoyed getting that walkthrough of the Koala paper from Jinyu and Ted. Thanks for sharing that. I think there's like obviously a ton of opportunity here, and like being able to bridge gaps between fields, whether it's probabilistic programming world, the like RL world, the like classic cognitive architectures and good old fashioned AI, and then like what people are doing in the like open source world and iteration on program flow around language models. Like I think that's super critical, and this like LangChain and Koala and language model cascades are three of my favorite examples of that kind of like cross pollination between these fields. So I had a great time in this webinar hearing from all of you, and tons of exciting questions in the Q&A and in the chat. And hopefully this spawns discussions offline, online, in the folks who attended and the folks who are watching the recording later, to like keep digging into these questions, into like what the cognitive architectures are going to look like, and how we're going to make them better.
And I want to thank Charles for moderating this. And I think he probably has he has to actually understand what's going on so he can ask good questions. And I think he somehow always manages to do that, which is incredibly impressive. So.
Thanks, Harrison. I'm just a man asking questions. That's that's just me. Thanks a lot.
That's hard. All right. Well, thank you everyone for joining. Thank you everyone for tuning in. Have a great rest of your day.
Take care, guys.
Had tons of fun. Take care, guys.